Hello guys, welcome back. So now the sim is done and I have a preview here. You can see we have some really cool smoke sim, and I really like everything that's happening here. I think there's a lot of interesting details that are really hard to achieve in general. This swirly part as well is really tricky to achieve, and the reason why it's happening is due to a lot of things. One of them is the temperature causing the smoke to rise, and then the stuff at the bottom is being affected more by the wind because it stays there more, so it gets affected more. And then we're getting this nice swirl here, this nice turbulence or tornado kind effect in this shadow that is masked by this smoke object, and that's really nice and realistic. I think it looks really cool. And then we have a lot of fine details as well in the sim, and this is just a preview. And once we start rendering this, we'll see more details. Now, there's a little bit of wispiness and smokiness that I don't like too much. You can see here, there's a lot of fine, very defined lines, and I think we can add one more turbulence overall to break all those details up. But overall, I think it's really nice, and I like the result. Cool. So what we're going to do now is we're going to take a look at the smoke solver settings and understand what's happening. And but before I do that, I want to explain something about the data and how it's structured. And in SOPs, we have the spreadsheet that shows the point and their values. In DOPs, the data is structured differently. So this is the geometry spreadsheet. And you can see we have the sim, and then we have relationship and a list of objects. Now, the data in DOPS is attached to objects. You first create a container, which is this guy, and then for that container, we attach the data that the solvers then operates on. And you can see we have a density field, we have divergence, we have pump, we have sink, source, temperature, val, temp val. This is for the self-advection, and all this, there's stuff that we've manually injected, like the density and val and temperature, and then a lot of the other stuff is auto-created by the solver for it to do its job. And this is how the data is structured. There's also a geometry section, which is where you will find any geometry available in DOPS. And you can see the values. This is the tank static geometry, and this is the ground plane geometry. And everything is categorized by type. So let's say we can import any of these fields to SOPs. For example, if we want to, we can import them here as well to process them and do anything we want. If we decided to analyze divergence, if we decided to analyze the pressure and compute something out of it and use it as a mask for another force, we can do anything with this data. And yeah, this is how the data is structured. And I want to talk about the settings for the smoke solver. I'm going to create a new one here. And if you guys remember before, we had the importing of data, the empty object with the density attached and everything, and then we did an advection using the advect field, and then we did a gas project non-divergent. I can't remember which version we used, but there's the gas project non-divergent, and there is a gas project non-divergent multigrid. The variational is for the flip solver when it's not used in the smoke sim. So these two are the options that we have. And then for the gas advect, we have allow self-advect for the velocity. Now I'm going to take a look at these settings and try to show you where they're coming from. Now the first tab is the time scale, and this is what is available in every single node. There is a time scale here, all of those linked to a single value that is here. And then the temperature, diffusion, cooling rate, viscosity, buoyancy, and buoyancy lift, buoyancy direction are coming from here. So the temperature field has a gas diffuse microsolver. So I'm going to create that, and then it's basically set to blur to diffuse the temperature field, and that's where the settings is coming from. The cooling rate is a gas dissipate, microsolver that is set to affect the temperature field, and this is the rate that you're controlling. Okay, that's what's in here. And then the viscosity is basically a gas blur, which blurs the velocity field to make it look more, to make it look viscous. It basically affects the velocity. And then the buoyancy lift and the buoyancy direction is a gas buoyancy microsolver that uses the temperature as its temperature field and the velocity. And again, as we saw, we can name that anything we want. And these are the two controls exposed. Cool. So that's done. This section here is something we're not going to be using. We're only interested for collision, and let me explain what that is. If you look here in the merge operation, when we click in the relationship, you can see there's all these different type of relationship. And you can merge an object and say, this object that I'm merging, I want it to be used as a sink relationship, or as a source relationship, or a pump relationship. And by default, all these options are off except collision. So all these three options are turned off, and we're not going to be using that. We're going to be sourcing. If we do any sourcing, it's going to be coming from this source volume object, which is the most the more efficient way of importing data. So we're not going to use this section. We only care about collision. And then the advanced tab is where we have the more advanced controls. Now, this external force, I'm not so sure what it's saying, that it multiplies the forces by the force scale field at each voxel. I couldn't find the force scale field anywhere, and I'm not so sure what DOP is doing. I personally never changed this, to be honest. And the next tab is the rest field, and this creates two fields, rest 1 and rest 2, and these two are basically a copy of the point position at a certain frame that they get vectored over time, and they regenerate every 15 frames or 50 frames and mix between each other. This is useful for mapping texture onto the volume and or creating any noise that you wanted to stick and follow the curvature of the volume. If you wanted to create texture or colors or things like that. We're not going to be using this. We're going to create something a lot more efficient. This creates two vector fields and an extra attribute, and we're not gonna store that much amount just to create texture. And then the projection. Okay, so this part is very important. There is these two guys here. There is the gas project non-divergent, and there is the gas project non-divergent multi-grid, and this is what these options are for. The PCG uses this, the gas project non-divergent, which is the default, and it's faster method, and then the second one is the multi-grid, okay, and it's this guy. And there is a multi-grid iteration, and what this does, it runs the gas project non-divergent multiple times. If you wanted to run it 4 times, let's say in one frame, you can set the iteration to 4. Okay, and the way and where this settings is coming from is using a gas substep. Sorry, a gas repeat solver. And what this does is you plug in whatever input you want, and then you can tell it, I want 2 passes, I want to repeat this 3 times, 4 times, and this is independent from the gas substep node. This is different from the min and max that we have in the gas substep, which we're going to talk about. So this guy is plugged through a gas repeat solver, and you can increase the amount. Now, setting this something higher to 2 will increase the time of the sim a lot, but the result will be much more accurate because it runs the gas project non-divergent solving twice, which is the most important step of the whole sim. I generally set that to 2 because the quality is going to be a lot higher overall. If you have time and can set it to something higher like 3, you will get much more interesting, much more accurate sims, and the velocity will not blur as much as if it's set to 1. And what I want you guys is, I'm going to list a few settings afterward that I want you guys to play with and try. And let's continue. So the next part is the gas advect. And let me create, actually it's here. So these settings, the advection, are what's inside, are exposed from the gas advect field. You can see here we have a single stage, modified McCormick, and then a BFCC method. The single stage is the fastest, but it doesn't produce a lot of interesting details. The velocity blurs quickly. And then the modified McCormick is the balanced version in terms of speed quality compared to this, compared to the BFCC. It's similar to the BFCC, but it's a lot faster. It's 2 times faster. I personally use BFCC all the time. I do not change. I do not use any of the other method, even though it's much. It's slower, not much slower, but the result is much more accurate and much more stable. And when you look at the details, so that's what we're going to be using. Now, there is a threshold. There is an error margin with all these solvers, with all the 3 advection type. And how you want to treat those errors is controlled here. So you can say I want to revert to, I think, revert to some, I'm not sure what to revert. Yeah, so the revert will use a previous value and a new value that you can control with the blend. So it blends, it smudges the error result. Basically, it blurs that. And then the none will not do anything, and then the clamp will clamp the error to 0. And that's what I use. I don't want to smudge the result. I don't want to blur the way the error is being handled. I want simply to clamp it, and that generally is, I found, much more stable and creates more interesting results. Now, the advection method, there is multiple types, and each one of them has different sub-steps. The single step is the cheapest and the least accurate. The trace is the best one in terms of speed and quality. This one is the slowest, and it quickly explodes the sim. And then these guys are 3 and 4 times slower than the trace. It basically runs the trace 3 or 4 times, and they are 3 or 4 times slower. I don't change this. I generally keep it to trace, and changing it, setting it to BFCC generally makes it work nicely. And that's where all these settings are coming from. Now, the advect CFL is this guy, and I don't remember what what's it's set for. I'll look this up and see. I never change it to anything else. I always keep it to this default, but I'll see if I don't think it affects the quality of the sim overall in any way, like these guys. And maybe you guys can also test this one. And then the correct collision. Let's see, clear the density field inside the volume mask at each step. Yeah, so every time you have a collision with the geometry or any other fields, there is a collision mask that gets created, and by having it turned on, it resets that collision mask to be accurate every frame, and we want that to be on. And this is if you create any temp field and you want to clear them out, you can do that here. And this is for slicing and distributing the sim, which we're not going to be doing. Now, where these guys are coming from, they're coming from the gas substep. Okay, and this gas substep, you can connect any number of micro solvers, as we saw, and you can increase how much steps happening. You can set it to a minimum of 3 and 3, and that will make the sim run 3 substeps every frame, and will make it 3 times slower. And then you can also set it between min and max, which will be decided automatically based on how fast the sim is moving, based on how fast the data is changing. So the DOP will automatically figure that information out and decides to use the the correct substeps based on the smoke behavior. And we're gonna see that how to use that efficiently. And then let's see what else. The CFL condition, this one I generally leave it to 1. When max step is greater, the solver uses this parameter to decide the number of condition is that no substeps can allow object to interpenetrate. Yeah, I think this is basically how far, if you have collision between fields, this is how deep they can collide. And currently it's set to 1 voxel. You can set it to a higher number, let's say 10, and that will give the margin, these fields to collide 10 voxels between each other. And we don't want that. We want every interaction between the fields to be accurate. So we're going to leave that to 1. And let's see. So this is pretty much all the settings available in the smoke solver, and this is what we're going to be using throughout this workshop. Now let me do something. Actually, let's move it here. I'm going to edit this guy, and I'm gonna dive inside. Okay, and I'm gonna start changing stuff. Cool. So let's go first. This is the input object. This is the pre-solve. This is advecting the velocity by itself, updating the velocity with the new forces. This gas viscosity we're not using, I'm going to delete. This is the temperature buoyancy, we're going to keep that. We're going to keep this guy. We're going to keep this guy. And then compute rest, we're not using this, I'm going to delete that. And then this is where it decides to use the PCG and or the multi-grid. It has this node to enforce boundaries, and then a gas feedback as well. Those are needed for the sim to work properly. And I'm going to delete everything except those. Okay. I also don't need the gas repeat solver actually, and I'm gonna remove that. I don't need the gas feedback. It's only needed to store certain information. We don't need that. I'm gonna remove this because this is what if you want to set the grid to run multiple times. So I'm gonna remove that, and then I only need this guy. It has 2 versions, one with OpenCL and one the default that uses CPU. So that's what I need. Then let's see, advect rest. We don't have any rest field. Diffuse, it diffuses the temperature. Let's keep that. We have it. And the advect field can advect multiple fields at the same time. So here it's advecting all those guys. Okay, that's correct. Clamp fuel, we don't need that. We need that. That's what decays the temperature. Actually, the decay of the temperature is not done using the gas dissipate, but we're gonna get to this at a more advanced level. And this is deleting the temp fields, the custom fields, and this is for the sourcing relationship, which we're not using. We're not using anything except the collision. So we're gonna keep the collision, which is build collision mask, which is this guy here. So I'm going to connect this. Let's delete all this section. Let's delete this. Actually, let's keep it in case it does a switch. And let's remove that node. That's where the sourcing is happening. And this is to collect certain data about the sim, so we're going to keep that. And this is a much more simplified version now. It doesn't have any of the extra stuff which we were not using really. So I'm going to copy the same inputs here, this guy here, this guy here, and then this, and let's hit play. Everything works. everything works, and the sim is most likely to look exactly the same. Well, it is going to look the same. I just need to plug in the collision if it still works. Yeah, it still works. I don't think it does. Anyway, the majority of the things we did, the sim is still working nicely. We're not seeing any odd behaviors, and we've removed all those nodes. We removed a lot of stuff here, and you can see we're just using a much more simplified version. Even though everything was off, we're using a much more simplified version of the smoke solver. And I think that's pretty much it. I hope this gives you guys an idea about the whole process. And then what I want you guys to do is, the very important part is these guys. So I want you guys, once you have a sim that you like, I want you to run a test with multi-grid iteration. First, set it to PCG, run a sim, set it to multi-grid at once, run a sim, and set it to 2 and run another sim, and have all those stored. And then the advection, run a sim with this advection with the multi-grid set to 1, and then change all of this to BFCC, and then clamp on all this and compare the result. And then last, once you're done, set this to 2, and then run a sim with 1, 1, and 1 here, and then run a sim with 2, 3 in these two guys, and have all these 5 different wedges stored and mark them so you can see the difference and understand how everything works. None of this will affect the sim unless the smoke is not rising to a much higher level, which will make the domain smaller so that you have less voxels to deal with. And I think that's pretty much it. Thank you guys for watching, and see you in the next video. Bye bye.